So the softmax and logistic functions allow us to go from log posteriors to posterior probabilities. So let's look at what we are doing when we talk about posterior probabilities, right? So posterior probability of a class given a data point is, by Bayes' rule, log of the probability of the data, the log of that basically, plus log of the probability of y equals k, and this is up to a constant, because remember we also divide by the probability of density of x, which we are just dropping from here. So basically, if I call this, I can call this L sub k, as something I've computed, and I've dropped a bunch of constants around the way. So basically, let me say that I'll look at all the constants I've dropped and model them by some alpha. Obviously, the constants I drop are independent of k, and so that's why alpha is independent of k, and that's super important. And note also that these posterior probabilities have to sum to 1. So this has to be equal to 1. And from that earlier equation, I know that these are e to the lk plus alpha. So alpha has to be what it has to be, right? E to the alpha comes out, and then I have k equals 1 to k, e to the L sub k, and that product has to be equal to 1. So this e to the alpha is 1 over summation k equals 1 to k e to the lk, and so now the probability that, and let me just switch notation, y equals j given x, which was, remember, e to the lj plus alpha, is just e to the lj over summation k equals 1 to capital K e to the lk, right? And this is our so-called softmax function. Why is it softmax? Because the exponential grows really fast, and so whichever of these lk's is the biggest will dominate here. So you will effectively, for example, if one of them is 20 and the other ones are like 1 or -1 and things like that, then essentially I'll have e to the 20 over e to the 20 plus smaller terms, which will go to 1, right? So if lk naught is much larger than lk for k not equal to k naught, then what we'll have is that p of y equals k naught given x will tend to 1, and of course the others have to tend to 0. And that's why it's called softmax, hence the term softmax. Right? It's a very, very standard box that we put at the end of stuff. So let me see what happens. So here are the L1 through L capital K coming in, and out come your estimates of the probabilities of p of y equals 1 given x, p of y equals capital K given x. So that's what the softmax is doing. Now in practice, these L's can be coming from all sorts of places. We will talk about logistic regression, where they're coming from a linear transformation of some feature vector, but that feature vector we can either make up on the spot, or it could, for example, come from deep neural network, and with the input being X, and this could be learned. So there's a bunch of different ways in which these L's could arise, but the concept of softmax is very useful and used very broadly. So now let's look at a simplification in a binary setting. So in a binary setting, we have class 0 and 1, and suppose my log of the probability of y equals 1 given x is, I don't know, I'll call it L1 plus alpha, and log of the probability of y equals 0 given x is L0 plus alpha. Well, in this case, I often define the log likelihood ratio, L, as the log of the ratio of these two probabilities, which is of course the difference of the logs. So this is log of the probability of y equals 1 given x minus log of the probability of y equals 0 given x. And note here that the alpha just cancels out. We get L1 minus L0. We don't get any nuisance terms anymore. So this is the form of the LLR that we use for binary classification. And we can ask again, how do we get back the probability of the raw posteriors back from this? And of course, we have the following thing that must be satisfied: y equals 1 given x plus the probability of y equals 0 given x is 1. And when we undo the log there, we have that the ratio of the two, y equals 1 given x divided by the probability that y equals 0 given x, this is e to the L. And so when we put these things together, we see that probability of y equals 1 given x is going to be e to the L over e to the L plus 1. And the other one, probability of y equals 0 given x, is of course 1 over e to the L plus 1, right? And we often look at this guy. It's enough to specify one of them because they add up to 1. We often look at this guy and we write it as 1 over 1 plus e to the minus L, and this is called the sigmoid function. So let me write it down more carefully. So the sigmoid function, sigma of z, is 1 over 1 plus e to the minus z. It converts LLR to the probability of class 1, right? And what does it look like? As z goes to infinity, e to the minus z goes to 0. And so sigma of z tends to 1. And as z goes to minus infinity, e to the minus z goes to plus infinity, and so I have 1 over infinity that goes to 0. And when z equals 0, I get this e to the minus z is equal to 1, so sigma of z is half, right? So that's what it looks like. So I have half at 0 and tending to 1, symmetric around half, and the asymptote here is 1, the asymptote here is 0. That is sigma of z. So the sigma is sort of the analog of the softmax, right? In the binary situation, it's a specialization of it where you realize that I only need to spit out one of the two probabilities because they add up to 1. For larger than 2 classes, we don't really bother to use it. We just spit out all k probabilities and constrain it such that it adds up to 1. So that's the sigmoid.